right, folks. Dr. Paul Cuban will introduce our next group.
Good morning, everyone. Yes, I am Paul Cuban. I teach primarily electrical and computer engineering courses. And I would like to introduce Jordan Weyer and Garrett Bielefeld.
Good morning. My name is Garrett Bielefeld, and I'm Jordan Weyer. And our project was the Solar Splash Instrumentation System. A brief introduction to Solar Splash. It is the World Championship of Solar Electric Boating designed for the college level team. Each boat is powered by a battery bank that is charged using solar power. It takes place over the course of 5 days, and they are tested on 7 different categories. 3 of the 7 categories are off-the-water competitions, and they include the technical report, the visual display, and the workmanship of the boat. Then there are 4 on-the-water competitions that are the sprint, maneuverability, endurance, and the solar slalom, which is a combination of speed and maneuverability. So USI participated in their first Solar Splash competition this past June. They started off with a donated pole, $2,500 from an Endeavor grant, and $4,000 in engineering department fund. They worked on this project for 1 semester, and it's normally a 2-semester project. They ended up placing 9th out of 17 universities, and they won 2 awards, the first being Outstanding Solar System Design and Best Rookie Team. The problem that the current Solar Splash team had was that they did not have a convenient method for collecting data. They could only measure the voltage, and that was by holding a voltmeter across the battery bank. They were not able to measure the motor speed, temperature, current, and light. And the operator also did not have access to these measurements while driving the boat, including the voltage measurement. So the goal of our project was to create an instrumentation system that can display several key parameters for the driver to view while racing and for testing. And this will be a huge benefit for future Solar Splash teams. These parameters include the voltage across the battery bank, the current being drawn by the motor speed in RPM, the temperature near the battery bank, and the ambient light near the solar panels. All of these measurements will be sending data to an LCD to be displayed for the driver to view. This will be done using an Intel Galileo microcontroller board based on the Intel application processor. The microcontroller is a special purpose computer which is dedicated to one task and runs one specific function or one specific program, unlike a desktop computer which is multi-purpose and can run multiple programs at a time. It is hardware and software pin compatible with Arduino, and because of this, the Arduino IDE is used for this project. And an IDE is a programming environment that allows us to write our code, and it uses the C programming language. It has pins 0 to 13 for digital inputs and 0 to 5 for analog inputs. And the Galileo board is intended to operate at 3.3 volts or 5 volts. And 5 volts is used for this project. Here is the Galileo board next to a nickel for scaling. On the Galileo board, we have the power supply ports, a USB or micro USB slot for uploading the program. Up top we have the 0 to 13 digital pins, and we have 0 to 5 analog pins down here, and there's also ground amongst other pins. Along with the Intel Galileo board, the team was also also given a growth starter kit. This starter kit consists of many different sensors and components that can be used with the Galileo board. For this project, we used the LCD, the I/O shield, temperature sensor, light sensor, and a push button. Additional hardware that was not included in the growth starter kit was a potentiometer, which is shown in the picture on the left, and that is used to measure the voltage. We have a shunt resistor in the top middle, and below that an instrumentation amplifier, which will be used to measure the current. And we have a magnet and switch in the right, and that will be used to measure the speed in RPMs of the motor. So the temperature sensor comes from the growth starter kit, and it uses a thermistor. The resistance of this thermistor increases when temperature decreases. So from this difference in resistance, temperature can be calculated. And this sensor will be placed next to the battery bank to warn the driver if they begin to overheat. The battery bank can output a maximum of 40 volts, and the Galileo board can only accept a max of 5 volts. Because of this, we had to drop the voltage down, and we did this first using the voltage divider circuit. This voltage divider circuit did achieve our goal, but did not reach the optimal voltage range that is 0 to 5 volts. It reached 0 to 3.6 volts. And because of this, we replaced the voltage divider circuit with a potentiometer, and the voltage is linear, so we were able to calibrate the potentiometer to reach that optimal range. And depicted in the pictures on the right, we have the voltage divider circuit in the top with the potentiometer circuit in the bottom. To prove that the potentiometer was in fact linear, we connected a 40.5 power supply to terminal 3 on the potentiometer, connected terminal 1 to ground, and connected terminal 2 to the input on the Galileo board. The power supply was turned on to 40.5 volts, and the potentiometer was calibrated by turning this until the Intel Galileo board read 5 volts. The power supply was then decreased by 2.5 volts until it reached 0 and we recorded the Intel Galileo board measurements with every increasing measurement. And as you can see in the graph, that the potentiometer is in fact linear. The slope of the graph is what gives us the inverse of the slope of the graph gives us a value of 8.1, which will be our scaling factor of the potentiometer. So if the Galileo board reads an input of 5 volts, you multiply that scaling factor to get the 40.5 volts on the actual input of the power supply. Yeah. For the motor speed measurement, we use parts from a bicycle speedometer. Those parts include a small magnet that would normally attach to one of the spokes on the front wheel of the bicycle, and the switch that would normally mount to the front fork of the bicycle and is activated by each passing of the magnet. But for our use, we will attach the magnet to the rotating motor shaft between the motor and the propeller, and the switch will be mounted to the shaft frame so that each pass of the magnet will activate the switch, sending pulses to the Galileo. The light sensor also comes from the growth starter kit and uses a light-dependent resistor, or an LDR.
And much like the temperature sensor, the resistance of the LDR will decrease when the ambient light intensity increases. So with this difference, with this change in resistance, ambient light can be calculated. This sensor will be placed next to the solar panels to measure the ambient light that the solar panels are potentially taking in. Pictured below is a close-up of what that light sensor looks like.
To measure the current, we put a shunt resistor in line with the motor and the battery bank. The shunt resistor has a low resistance and can handle a high amount of power, which is perfect for our needs. The shunt resistance is very small, so the drop in voltage across the shunt resistor will also be very small. And to be able for the Galileo board to read that voltage drop, an instrumentation amplifier is used to boost the voltage. Then the current can then be calculated using Ohm's law, since the voltage and resistance is known. Here is the hardware setup of the current measurement system, with 40 volts being the battery bank, in series with the shunt resistor that's connected to the motor. The instrumentation amplifier will be placed to get the voltage drop across the shunt resistor, boosting that voltage, and that will be displayed on the Galileo board.
Here's a block diagram of how all of the measurement hardware will be connected. At the top center, you have the auxiliary power, which will be a 12-volt battery, and that will supply power to the Galileo board. Since the Galileo can only handle 5 volts, a voltage regulator will be placed between that 12-volt battery and the Intel Galileo to drop down that voltage to the acceptable 5 volts. At the top right is the battery bank. Connected across the battery bank is the potentiometer, which is used for the voltage measurement. In series with the battery bank and the motor is the shunt resistor, and that will be used for the current measurement. The magnet and switch will be connected to the motor shaft to give us our motor speed measurement. The voltage measurement, current measurement, and the motor speed, along with the temperature sensor, light sensor, and button, will all be sending data through the I/O shield to the Galileo to be processed, back through the I/O shield, and then to the LCD to be displayed for the driver.
Here is what Garrett just explained on the actual Galileo board. Here we have the button on the left, the LCD, the light sensor and the temperature sensor, potentiometer on the top, and magnet switch. All that goes to the shield, and then that is connected to the Galileo board. The current is not displayed because we did not get those parts in on time.
So an introduction to how our software works, the LCD will cycle through displaying each measurement for about 1.5 seconds each. So it will display the voltage measurement for 1.5 seconds, then the current measurement for 1.5 seconds, and so on, until the button is pressed. Once the button is pressed, it will show just the voltage measurement until it is released. Shown below is a close-up of what the push button looks like.
To reiterate what Garrett just said, if the button is turned off, it'll go down this cycle. It'll first go to voltage, check if the button's on. If not, it'll continue down. If the button is pressed, it will display voltage until the button is released, and then we'll continue showing the other measurements.
So the temperature sensor from the Grove starter kit originally calculates temperature in Celsius. So in our code, we converted Celsius to Fahrenheit. When it is displayed on the LCD, it is displayed with a blue backlight for normal operating temperature conditions for the batteries. Once it reaches dangerous levels of heat, then it is displayed with a red backlight purposes, this was first set to 80 degrees, but it has since been set to 120 degrees. And pictured over here, you can see the difference, blue backlight for normal conditions and a red backlight for dangerous conditions.
From the potentiometer, the voltage can be directly measured by connecting it to the shield. The voltage input will be between 0 and 5 volts. The code will multiply the voltage in that range by the scaling factor of 8.1 from what I discussed earlier, from the inverse of the linear slope of the potentiometer. And that is done because that will display the actual voltage instead of the decreased voltage. If that voltage measured across the batteries is less than 30 volts, the LCD will turn red, like how the temperature sensor turned red when it was placed over 80 degrees Fahrenheit.
For the motor speed measurement, the Galileo will detect a pulse each time the magnet passes by the switch. So one pulse represents one revolution. It will also measure the elapsed time between each pulse. By using this elapsed time between each pulse, the motor speed can be calculated. This was first simulated using a function generator generating a pulse function, and the Galileo detected these pulses and displayed the speed in RPM. We first set this to a 50 hertz pulse function, and that translates to 3,000 RPM, which was displayed by the Galileo. So the frequency was turned up, and the Galileo was able to match the output of the function generator up to 10,000 RPM. So we then tested with the magnet and switch. To do this, we attached the magnet to a rotor of a DC machine in the power lab, and the switch was held next to the rotating magnet to send pulses to the Galileo. The Galileo then displayed the motor speed in RPM, and to verify the accuracy of this reading, we used a strobe light tachometer to measure the speed of the rotating shaft. And the Galileo was accurate up to 2,000 RPM, which is perfect for the speed of the boat motor. This has not been tested on the boat motor because it is currently disassembled.
A light sensor value correlates to a lux value. And the lux value, a lux value of 1 will have a sensor value of 200, and a lux value of 3 will have a sensor value of 300. As you can see, the relationship between the lux and sensor values are not linear. So because of this, we decided to just display the sensor value instead of changing the code to display a lux value. Since the light sensor value will have a large number because it tests the ambient light, and as the light intensity increases, the sensor value will also increase. And we are going to be reading a direct sunlight reading, which will have a sensor value of about 1,750 to 1,900, but we were not able to effectively measure this light sensor value because of the time of year.
For the current measurement, the Galileo will measure the voltage coming in from the instrumentation amplifier. This will be done exactly how the voltage was measured, which Jordan discussed earlier. So knowing the voltage difference, the resistance of the shunt resistor, and the gain value from the amplifier, current can be calculated using Ohm's law. But parts did not arrive on time, so we were unable to test or simulate this.
For the economic considerations, if we were doing this for a design firm, we would be projected, or we would be expected to get paid, and Garrett and I worked on this project for a total of 100 hours each for the whole course of the semester. We would be expected to get paid about $15 per hour, and so that total is $3,000. Dr. Cuban, our advisor, would be considered the project leader, and he would be expected to get paid about $150 per hour. He worked on the project an hour a week, totaling 16 weeks, so that total would be $2,400. We also had the parts that we ordered in the economic considerations with the highest priced parts being the Galileo board and the Growth Starter kit. We also ordered the shunt resistor, voltage regulator, and instrumentation amplifier, and multiple of these were ordered in case they would burn up and they needed to be replaced. We also ordered multiple different types of instrumentation amplifiers in case we did not get the desired output we wanted from them. The total of the parts list ended up being $203.34. So our grand total would be $5,603.34.
So a quick summary of our work. 4 out of 5 measurement systems were successfully simulated. Again, current was not because parts didn't come in on time. But the other 4 were only simulated using lab equipment and not tested on the boat because the boat is currently disassembled. But we believe that this instrumentation system will greatly benefit future solar splash teams.
Some recommendations for the future solar splash teams. The Galileo board needs to be placed in a waterproof box and mounted to the boat so it is user-friendly by the operator. It'll need longer wires so that will be attached from the Galileo board to each instrument, to each measurement device, and the code will also need to be tested with the shunt resistor and the instrumentation amplifier when those parts arrive.
So first of all, we'd like to thank Dr. Cuban, our advisor, for all of his hard work and contributions to this project. We'd also like to thank Dr. Deersing, Dr. Mitchell, Ms. Moore, and Mr. Amos for their contributions and help along the way. We'd also like to thank the Intel Corporation for donating the Galileo board and the Growth Starter kit. And lastly, the previous Solar Splash team for laying the groundwork for our project.
All right, questions?
What causes the battery heat to go up, and what would they do in a race to compensate?
Battery will heat up whenever a load is applied, and so there's not much that they could do during the race. It's merely for warning purpose.
They do have an onboard fire extinguisher in case something bad would happen. So,
But that would be unexpected. Battery overheat.
So aside from the nice project, by the way, and I like the instrumentation. I was there for at least one of the days last year for the Solar Splash, and I think it's a neat addition. But I have a couple questions. Aside from the fact that it came with the equipment, how did you pick the light sensor for this application? Was it, let me ask it as a true-false question. Was there any consideration made to the selection of the light sensor other than the fact that it came with the kit?
no, there was not.
Okay, because from your table, it looks like that might not be the right light sensor. It looks like that light sensor is particularly calibrated for people playing on Christmas morning with a new toy, and so it's highly sensitive in the low ranges. And what we're actually interested in on the solar is the high ranges, and so that might that might be something that could be a consideration or at least a recommendation to see if there was a better one. And ergonomics of a display. How did you come up with the procedure, your flow chart there? How did you come up with just cycling cyclically through? And what other considerations did you make for the driver? That was
For this?
Yeah. How did you arrive at this diagram?
Well, we decided to display voltage primarily because that is what's going to be powering the motor, and that's the most important reading. Other
Okay.
yeah.
I'd just like to recommend that it's one thing to be able to program devices that do great things. It's another thing to make them human accessible. And the difference between a lot of cell phone technology, right? The breakthrough that iPhone did was not in their ability to communicate to the cell tower more effectively. It was in their ability to make a 2-year-old able to understand how. And literally, my 2-year-old figured out how to open my wife's cell phone and get to all the apps he wanted to, right? And so my recommendation maybe would be, the button could be used to speed up the cycling process. So the driver's in the middle of a race, and he wants to see either the motor speed or something. He might be able to get quickly to something. And there's ways of making that would just be my default. But, maybe you hold it, you get the voltage because that's what he wants to see the most often. But if something sounds funny and he wants to get to the motor speed all of a sudden, you can push it 3 times and there you are. That would be my suggestion. But I think it's an error to ignore the human interface part of any microcomputer, because that's critical to the success of the thing, because that's what someone's going to interface with. But that was those were my questions.
Yes, my question leads off exactly from what Professor David was talking about. That was the idea of concept of operations. How much thought did you give to operations, actually using this device, the ease of using it, the ease of seeing it in the dashboard or wherever it is? I think that's an important piece here, and I wish we would have maybe spoken a little bit more about that at the beginning, but of course, you got a lot to do to even get to this point. So the question is, what are your thoughts on operations as someone actually operating with this?
Can you repeat that?
So what are the plans for installing this and testing it with an operator, adjusting the light level, adjusting the placement on the dashboard? The issue is operations, concept of operations.
In our code, we commented the areas that would need to be adjusted. So once the Solar Splash team actually utilizes this instrumentation system, they will know what values they should be getting, and then they could alter the code to make it more user-friendly for them.
Does that answer your question at all?
It helps a bit.
So I may have a different way of asking that. In terms of improving next year's Solar Splash boat, was there any consideration made of where the parts will be located? Any consideration for it needing to be waterproof? Where does it need to be located on the console next to the steering wheel? Was any of that put into a process or thought of during your senior design? showed, but making sure the sensors are in the right locations, making sure your LCD screen's in the right location, were any of those parts thought of?
No, we did not consider exact locations. We just know that the light sensor should be placed by the solar panels, so it's getting near the same light reading. And then the LCD should be placed hopefully inside a waterproof container along with the Galileo board, and that should be mounted on the dash right there for the driver to view. Other than that, we did not test exact locations where the sensors should be placed.
Continuing on with that question a little bit, in terms of all of your components, the light sensor, the instrumentation amplifier, did you go through a process of selecting or choosing the proper pieces? You've already spoke of the light sensor a little bit, but in terms of the instrumentation amplifier, the thermistor, and the temperature sensor, were there any considerations made in the selection process of all those individual pieces? And it's okay if it's how the board came at this point.
Yeah. The Grow Star Kit included the temperature sensor, the light sensor. But for a potentiometer, we had one on hand, and that worked for this project, so we went ahead and used that. And for the shunt resistor and the instrumentation amplifier, we ordered the parts that met our specific range.
So at this point, it was kind of, let's spend the least amount of money, get a very rough prototype up and running, and then next year's Solar Splash to implement the proper components and do testing in terms of improving the overall design.
Do you know how far the runs will be to the various sensors, like the light sensor and the current sensor? And you consider the fact that you may get noise induced in those lines, which would throw off the readings?
No, we did not take actual measurements. Most of the code was disassembled, so we couldn't hook anything up and take exact measurements.
You also mentioned that, of course, the Galileo and the display should be waterproof boxes. What about the sensors themselves? Like that solar sensor, for example, is going to be on the roof. Water can get splashed on that, which would short it out potentially or throw off the readings or damage it over time.
Yes, that's definitely another consideration. At the time, we don't know how we would make it waterproof without compromising its functionality or its accuracy. So if we tried to place it in another waterproof box, it wouldn't have the same light reading, and same with the temperature sensor.
What about the potentiometer? I mean, that has the potential of rotating under vibration, which would throw off its calibration.
The potentiometer has a thing on it that you could turn, and it will keep that at that certain measurement. But we wanted it to be able to be calibrated in case it would move, where we could just hook up a voltmeter across the battery bank, and if that reading is not the same as what's displayed on the Galileo, we can turn the potentiometer to get that reading.
All right, folks, let's give them a hand.